Okay, we got this bell work solve, negative 2x equals 14. And to solve this one, we're just going to make that a 1x instead of a negative 2x. So this is what we want. And the 1 is called a coefficient. It's the number being multiplied by a letter. Right now the coefficient is negative 2. We're going to force it to become a 1, and we use the principle of equality to do that. That's the division principle of equality, which tells me if I do something to one side, I must do it to the other side as well. So to make a number a 1, in this case the coefficient negative 2, you just divide it by itself. And if you do it to one side, you got to do the other side. Negative 2 divided by negative 2 is 1, which we're already showing as a coefficient of x. 14 divided by negative 2 would be negative 7. And then we can check. You could say negative 2 times negative 7. Put that in the calculator, and you will get 14. So this is our solution to the equation. Remember, a solution is a value you can replace an x with or a letter with, and it makes the equal sign a true statement. Meaning if you replace the x here with anything but negative 7, you would get a false statement. But the only one we can think of right here is negative 7 to make it true. There's our 3 objectives for the day. I can remember how to solve equations. I know the 4 signs of inequality, and I know that an inequality has infinite solutions and that a graph represents all of the solutions. So take a minute, write those down, then we'll get started. So we've seen this before, all of this stuff, and we should already know how to solve equations. Solving equations takes us furthest back into Unit 1, but we've been using all the principles of equality as we've went through as well. So none of this should seem very new. We'll get to this stuff here at the bottom, but first, kind of like the steps we take in order to solve equations. So first up, we would have distribution. If there is any distribution, then you're going to see some parentheses in the problem. Now, distribution, from what we remember and what we've been doing, is just another way to say multiply. So if you have a number on the outside of the parentheses, you need to multiply it by everything on the inside of the parentheses, all the terms, okay? So we should only be dealing with maybe 2 terms inside parentheses, but it's possible in the future you may have 3. Now, just like the bell work though, there was no distribution on it. So we may not see actual need for distribution in some of the problems. So be ready for that. We may be able to just skip this step from time to time. Who knows? Step 2, again, there was none of this on the bell work either, but sometimes it is skipped as well. We're just looking for like terms to combine on either side of the equal sign. We can't cross over the equal sign yet. That's what step 3 is going to be, but step 2 here, combine any like terms, x terms with x terms, constants with constants, no matter how many there are, you combine them. Now that's going to make the problem smaller, which is why we call that combining like terms. Is really just a form of simplifying the expression. If I can spell simplify, there we go. Okay, so combining like terms is just a way to simplify the equation. Step 3 kind of does the same thing, but it does it in a different way. So step 3, that is when we isolate the variable. And we isolate the variable with either addition or subtraction principles of equality. What we're doing when we isolate the variable, and we've seen this many times already, is we make zeros. So again, we did not see this step either in the bell work. We did not need to make any zeros to isolate the variable, which means really just getting the x or whatever the variable is on its own side of the equal sign. So if we see x is on both sides of the equal sign, or numbers on both sides of the equal sign, we got to zero stuff out. And we'll go over that, which we have, but it'll be a nice review. And then finally, we will force the coefficient to be 1, which is what we did on the bell work. So we're just making ones. But specifically, it's the coefficient, right? So that's our steps. Again, the first 3, sometimes they're just not needed, but the 4th one almost always is needed. But even then, sometimes it's not. Okay, so on these principles of equality, we got addition and subtraction, and just like we're showing above in the steps, we use addition and subtraction principles of equality to make zeros. Now, the reason why we would want to make zeros is because if we can, then we get to ignore whatever value is there. And that will isolate the variable, meaning that if I have something being added or subtracted to a variable, then by making a 0, I get to look at just the variable, right? So in the past, these principles of equality, we kind of show them a little bit like this. So it's remember we draw a line through the equal sign like this, kind of, and then we draw a line here. That arrow brings the equal sign down. And the way we structure it like this is so that we have a little bit of order and structure to the way we're solving these. Because now I'm looking at this line, which represents the equal sign. If I do something on this side of the line, on the left, I've got to do the same thing on the right. Which is true if I do something on the right, I've got to do something on the left as well. The same thing on the left. So we'll use addition and subtraction on both sides to make zeros. And then, like we see on step number 4, we tend to just use division for our fourth step. But it's possible from time to time that we may need to use multiplication to make a 1. But these two principles of equality are strictly to make 1s. But again, it's a focused process, so we're not just making any value 1s. We're specifically making the coefficient a 1. Okay, and again, just to reiterate this from the bell work, the coefficient is the number being multiplied by the letter. So, if we saw something like 2x, it would be an effort to make the coefficient, which in this case is a 2, to make it a 1. And we do that simply by dividing it by itself. This is the process for solving equations, which we've seen many times. Here's a nice review. The reason why we're doing this is because this unit is based on inequalities, which we're not going to be using these today with inequalities. We're going to do a quick review on equations, but this is to prepare us for what we'll see on Monday for us, which is next time. All right? So all this stuff we're going to review again, but for now, this is what we got. So this problem, let's go ahead and solve it. And to solve it, I don't see any distribution, okay, because there's no parentheses, so we're going to skip that garbage. And I also don't see any like terms that I can combine. Some students may say, well, 57 and negative 47. That's true, but they're on opposite sides of the equal sign, so I can't combine them directly. In order to combine those, I will need a principle of equality, and that's what we're going to do next in order to isolate my negative 8x's, okay? So again, there's my line that brings down the equal sign. And in order to isolate my negative 8x's, I cannot have this negative 47 there. Now in the past, we would generally say put an x and a number like this. And I'm choosing to put the x's on the right because the x's are all already on the right. So the negative 47 has to be zeroed out by adding 47. But if I do it to one side, I must do it to the other side as well. Okay, so again, the setup with the line is to tell me if I do it to one side, I got to do it to the other side. Also, so from left to right, 57 plus 47, you can just put this in the calculator. We should get 104. Negative 47 plus 47 zeroes out as planned, and then I can drop my negative 8x's. Okay, because now that I've made this a 0, just like in the past we've talked about, I don't have to see it there. You could say that there's a 0 right here, but I don't want to see it, and I assume you don't want to either, so we don't have to show it. Now that has isolated the variable, meaning I've got all my x's on the right and all the numbers on the left, but the last thing I want is a coefficient of x that is a 1, positive 1x, not this negative 8x. So how do you make a negative 8 a 1? Just be careful because some students would say something like you'd add 7. No, we don't want to use addition to make 1s. We want to use division. So I'm going to divide it by itself, negative 8. But if I do it to one side, I got to do it to the other side. So negative 8, actually we'll do 104 divided by negative 8 first, which should be negative 13. And you can check that in the calculator. But negative 8 divided by negative 8, again, that becomes a 1. Now I'm crossing this out with a 1 to show that we're creating a 1 coefficient. Some students don't like to show that 1, so they make it a phantom 1, and that's okay if you do. I'm going to keep it just so we know that that's actually what we're trying to get. is a 1 coefficient. So does this work? Now I'm not gonna show the work for this, but in my calculator I would do negative 47 minus 8 times negative 13, and then I would just check to see if it gives me 57. So I just type the whole thing into the calculator. When I do, I get 57, and that tells me that we have actually found the solution. So again, this means you could replace this x with any other number than negative 13, but it would be a false equivalence statement. So this one right here is good. It's the only value that works in this equation. Actually, you know what? Take a minute, try this one out, and we'll go over it, okay? See how you do. Make some mistakes. If you do, that's good. If not, that's okay too, but we'll go over it. 1 minute. So let's see how you guys did. And the first thing I notice on this one is that we do have a set of parentheses, so I am expecting some distribution, which is just multiplication. Now, even though the multiplication sign is not shown, you can if you'd like, but it is about right there, okay? So I'm going to start out by distributing my 4 first to the 3y, which means that I'm going to take my 4 and multiply it by 3y's. So how many y's would this be? 4 times 3, 12. 12 y's. Now that's my first distribution. There's another set of distribution here from the 4 to the negative 4. So that would be the same as 4 times negative 4, which is negative 16. Now that's all the distribution we got because we do not distribute the 4 to the 44 because it's not actually being multiplied by the 44. And that's where we got to separate this, which means that I'm just going to write the rest of it as equals 44. Now distribution doesn't necessarily simplify, but it allows us to combine like terms if we have any. Right now we just got the 12y minus 16 equals 44. And even looking at this, there are no like terms to combine on either side of the equal sign. So we get to skip that step, which means we're going to go straight into principles of equality. Now again, you could say x is on the left, numbers on the right. We don't necessarily need to do that because all the, well, I guess it's y's. Try to use the right letter. So all of our y's are already on the left, so I don't really need to worry about the sides. But what I notice is that I got a negative 16 with my y's, and I can't have that in order to solve my equation. So I'm going to take that negative 16 and zero it out. And to make it 0, you just pretty much add 16 right here, okay? But if I do that to one side, because I've done this on the left side of the line, I must also do it on the right side of the line. Okay, so our arrow or a line brings down the equal sign. So let's go through each term. 12y is being dropped. And we wanted to drop it by itself, which we've just done, because negative 16 plus 16 is 0. So that has zeroed out as planned. We had planned that before. We shouldn't be surprised right now that it is a 0. But then over here, we've got the 44 plus 16, which would add up to 60. Now, this 60 that I get, there's no expectation that you do this in your head, or even that you do it by hand by carrying the 1 or anything like this. Just put it in the calculator, 44 plus 16, get your 60, and call that good. But it's not finished. Even though we have isolated all the y's on the left and all the numbers on the right, the y's are by themselves, the x's, or the numbers rather, are by themselves. But what we don't have is a coefficient of y that is a 1. And that is what we do want. So, right now it's a 12 in red. I want to make it a 1 in green. The color doesn't matter, but I'm just going to make it switch. How do I make a 12 a 1? I just divide it by itself. But if I do it to one side, here, divide by 12, I got to do it to the right side as well, divide by 12. So in the calculator, I put 60 divided by 12, I get 5. Now again, we can check to make sure this is actually the solution. I can go back up here to the top, and I can say, you know what, the y, I'm pretty sure it's 5, and then I can see what happens. This would be an order of operations thing if you're not using a calculator, though I do recommend using a calculator. So I would do 3 times 5, which is 15. 15 minus 4, which is 11. And then 11 times 4 is 44. So it does check off. We have, in fact, found the solution to this equation. Now, 5 is the only solution to this equation. Any other value, if you were to replace y with any other value, any other number, you would get a false statement, which is what we don't want. It's very large, but if we stick to the process, then we can kind of ignore some of these parts. Meaning, right here, I see distribution, right? Now, in order for us not to be overwhelmed by this, which sometimes we do, You can pretty much ignore the rest of that. It's still there. We just don't want to look at it because it could distract us from what we're trying to do. So right now we're just trying to distribute here. And first off, I would start with the 2 distributing, which is multiplication. So that would be 2 times negative 2x's. So again, how many x's is that? It's negative 4x's. But then we'll distribute the 2 to the positive 2, and 2 times positive 2 would be positive 4. Now we can't distribute anywhere else because there is no parentheses, and that 2 only applies to that set of parentheses. It's only being multiplied there. So let's get rid of the box so we can see the rest of this stuff. And then let's bring this stuff down. Okay, so again, none of the rest of this stuff really changed. All that changed was the distribution. Now, did it really simplify? It did not. But that's where we have this combining like terms, which will simplify it. So, simplifying, combining like terms, doesn't matter which one you start with, but I notice I've got these negative 4x's and these 3x's right here. So we would say, how many x's is that? Well, negative 4 plus 3 is going to be negative 1x's. Now, some students wouldn't show the negative 1, but they would keep the negative, and that's fine. I'm going to keep both. But then I've also got 4 plus 3, and I know that 4 plus 3 is going to be positive 7. The rest of that stays. So I now have negative 1x plus 7 equals 37 plus 2x, which is much smaller than what we had here and what we had here at the top, right? So we had these two, they were quite large, but now we've simplified it to something like this, which hopefully makes that a lot easier to work with. Now the difference between what we have now and the last 2 problems that we've done is that I have x's on both sides of the equal sign. So I'm going to have to zero out some x's in this process. Now if I have x's on both sides, I like to put the x's on the left, and then I will put the numbers on the right, but some students like to switch that, and you can. You should still get the same answer no matter which side you put the x's on. So let's go through these and see if they're on the correct side, because if they're not, we'll zero those out, we'll get rid of them. So negative 1x, it's on the x side of the line. Okay, it's good, it can stay. We don't have to do anything with it right now. The plus 7 does not have an x, so it's on the wrong side of the line, so we will zero that out by subtracting 7 from both sides. So 7 minus 7 will be 0, but if I do it to one side, I got to do it to the other side. So we know some of these values, but I'm going to go from left to right. Negative 1x is just going to drop, so it stays negative 1x. 7 minus 7, zeroed out as planned, so that we don't have to look at that crap anymore. Then we've got 37 minus 7, which if you put in the calculator would be 30. And then the 2x, which we still have, just drops. Okay, so we're close to isolating the variable. We've got all the numbers on one side, but now I have this 2x on the right side. So again, going through each term, I've got the negative 1x on the x side. That's okay. The 30 is just a regular number, so it's on the correct side. That's all right too. But the 2x has an x term, so it's on the number side. That can't happen right there. So we'll have to zero that out. We'll have to zero that out as well. So to zero that 2x out, all we're going to do is subtract 2x's because it's positive. So if I subtract 2x's there, it will zero out. And then on the left, I've got negative 1x's minus 2x's, which would result in negative 3x's. And then this would equal, we'll just drop the 30. And we didn't operate at all with that green 30. But at the tail end of that, we have 2x minus 2x, which was planned to be 0. We wanted that to be 0. It is 0. There's still a plus 0 there. I just don't want to show that garbage, okay? Which now, this has isolated the x's on one side, and then it's put all the numbers on the other side. The last thing I need from this is to make the coefficient of x a 1. I want this to be a 1x, not a negative 3x's. So, how do you make a number 1? Just simply divide it by itself. That's the fastest way it's going to happen. But if I do it to one side, here on the left, then I must do it also here on the right. 30 divided by negative 3 is going to be negative 10. Now, I did this earlier, but if you were to replace the x's here, all 3 of them with negative 10, and you were to calculate the left side, you would get 17. If you replace the x on the right with negative 10 and then calculate that, you would also get negative 17, which means that you actually have forced that equal sign to be true, and that also means that we have found the one solution to this equation. This is kind of a long problem. I don't think that anything in here was exceptionally difficult. Even though like we're combining x's here, it's really just negative 4 plus 3. That tells you how many x's there are. Or 2 times 2 is 4. Again, that's not exceptionally difficult. Or zeroing out values. Hopefully that's not exceptionally difficult at this point. If it is, then you guys need to be asking questions. But the truth is, if you can do all of this stuff that we just did, then when we get to an inequality, so later on, not today, but next time they're going to replace this with an inequality, we can do it. Because we essentially treat it like an inequality all the way down, except at the very end, which we'll talk about next time. Yeah, so here's our inequalities. An inequality is just a math sentence that compares values. Hopefully we've been familiar with these at least a little bit, or have seen them. At least the first two. If you've seen these first two, then usually the second two come in pretty easy because there's not much else to them. Now, just as a quick gimmick, though, because gimmicks, I don't know, math people love gimmicks. But you see how less than starts with L, and then the symbol kind of looks like an L right there? That's one way you can know that it's a less than symbol. But it's also kind of corny, so whatever. In fact, the greater one, the one that's greater than, right here, see how it starts with a G? So if you were to take the greater than symbol and just kind of put a hook on that, then it kind of looks like a G. Mine looks like an arrow, well, a really crappy one, but either way, I don't really care how you memorize that. Just we need to be able to interpret these symbols if we see them, because this is kind of like math hieroglyphics in this stuff. It's just another way to show symbolically or mathematically as a hieroglyph. We're using the symbol, the hieroglyph, instead of the words, because I don't know about you, but I don't want to write less than all the time, the actual words, because this is a lot more writing than this. And especially when we get into these, that's a lot more writing than just these two symbols right here, okay? So these two symbols, again, they may be new for us, but this one, see, it's the less than symbol, but it's got the little mark there in the bottom. That represents the equal to part of this symbol, okay? Now notice that this statement is an or statement because you can never have a value that's both. And some students get this mixed up where they're like, it has to be both. No, you can't be both. You can never compare one value that is both less than and equal to another number. It can only be one or the other. So if it is one or the other, then it is a true statement. So let's stick with this symbol. It's a less than or equal to symbol. And it's less than or equal to. There's the two parts. So if I were to compare this, less than or equal to, let's compare it to a fairly easy number like, I don't know, 50. Okay, 50 seems fairly easy. So, if I were to replace a value here and compare it, let's say I was comparing 8, I don't know, randomly. This right here is a true statement because 8 actually is less than or equal to 50. Now, is it equal to 50? It is not equal to 50. So this part is false, but it is less than 50, and that's all we need. It only needs to be one or the other. It cannot be both. So this is a true statement, and it's true as well if I make it like negative 18. This is still true, not because it's equal. That part's false, but this one's true, which makes the whole statement true. That's all we need, okay? And if I were to take this a little bit further, and again, I'm just doing this on purpose, but if I were to compare this 50 to 50, now the equal part is true, but the less than part is false. Again, we only need one or the other to be true, and even though the equal part is true, now the statement is true. Okay, so keep that in mind with these. This is two conditions. It has to be less than or equal to, but it only needs to be one or the other in order for the statement to be true. And then this one, again, there's our greater than symbol, but the little mark underneath it tells us that it could be equal to as well. So let's go ahead and read these inequalities, and then we'll determine if they're true. So I would read this out loud. I'm going to write it too. But this reads, negative 17 is greater than 15. Let's write that out. Okay, so that is a statement in words. You don't have to write this down, but you're welcome to. So that's how it reads. Now we're going to determine if that actually is true. So is negative 17 actually greater than 15? The answer to that is no, which means that we're looking at a false statement. Okay, and it's okay that it's false. It's just a nice statement to say, okay, we know that negative 17 is not actually greater than 15. If we were to replace that greater than symbol with less than, then it would be true. But as it is false, because that is never true. In fact, negatives can never be bigger than positive. So this one automatically is false right here. All right, so let's look at this next one. This reads 40 is less than or equal to 210. So I'll write this out too. There we go. So, is this true? Yeah. Now, is 40 equal to 210? No, it is not, but it is less than, and that's all we need for this one to be considered true. That's it. All right. Now, I guess we'll get into that. But the next part here, it says negative 6. This reads negative 6 is greater than or equal to negative 6. Okay, there we go. Now, this one is true, but it's true for a different reason than that last one was, because negative 6 is actually not greater than negative 6. That's false, but the equal part is what makes this true. Now again, just a quick hypothetical is if there was no equal sign on this, it would be false. Okay, so if it was just written as negative 6 is greater than negative 6, that would be a false statement because negative 6 is not actually greater than negative 6. But since now the statement is including the equal sign, okay, we're good. On this one, we're going to find a value for x that would make the inequality a true statement. So this reads x is less than or equal to 17, or it could just say some value is less than or equal to 17. Okay, now, can we find a value that would make this true? 1 works. 5 is good. Okay, 1 and 5 would work. As it turns out, 17 would work. Now, again, the 17, it doesn't make it less than. 17 is not less than, but it is equal to. So 17 technically is the biggest value we can use. But we need something that's less than 17 as well. So 17 works, but anything less than, which means that we could include, if we wanted to, 10, maybe even like negative 8. In fact, any negative works, including, let's say we wanted to compare negative 1 million, like this. Okay, now negative 1 million seems like it's quite large, but as a negative, it's not even close to being as big as 17. So this, if you were to replace x here with something very large like negative 1 million, this would still be a true statement, okay? Now, we've only listed, what is that, 6 values? It says how many values can make the statement true. As it turns out, there's an infinite number of values that make it true. And that's where we get into graphs, which is part of our objective, because I don't want to list all these infinite values, right? I didn't even want to really list 6, but it kind of emphasizes the point. But since there's an infinite number of values, we definitely can't list that in a listing like this one, kind of like we would with domain and range. But there's an infinite number of values, so we have a different way to express that. That's where the graphs come in, like the objective set. But before we get into that, here's this problem. Find a value of x that would make this inequality true. Okay, so take a look at this one. Think about it. What value, can someone give me a value that we could replace it with that would make it true? Yeah. Yeah, very good. All of those would work. So 5 would work. Now again, 5, it doesn't make 10 greater than 10, but it does make it equal, and that's all we need. But yep, anything going down from there. 5, 4, 3, 2, 1, and then I'm just going to put 3 dots, because this pattern would continue all the way down to negative infinity. But again, this is a great point because all the values less than 5 will, 5 or less would make this true. So since, again, all the values less than 5 means that there's an infinite number of values that would make this true. Now that one, perhaps we can do in our head. Like I said, next time, well, we'll be doing that type of inequality with principles of equality, okay? But for now, it's important for us to understand, yeah, there's lots of values that would make this true. Here we only have listed 5, and that's okay. Along these lines, if you wanted to, for some reason, if you wanted to switch the way an inequality is written, like this one, this would read x is greater than 100. It is exactly the same as 100 is less than x. Okay. Now we can interpret this. We could say, look, x is just some value. So any value that's bigger than 100 would make this true. Okay. Now at the same time, this one would read 100 is less than x, which means that 100 has to be less than any value of x. Again, you could reverse that and say, well, then x has to be bigger than 100. That's true. And to go back to elementary, which I'm not so excited about reminding people of, because we should be adults by now, it's kind of like the alligator thing, like they're saying right here. This one's showing that it's eating the x. So if this is a true statement, this is exactly the same statement because the alligator thing is still eating the x. I will not be referring to this as the alligator thing ever again, because we are adults, okay? But for now, hopefully that helps us to understand. You can switch them if you need to. So when we graph these on a number line, which is one of our objectives, it's only two parts. We need to know if we're going to put in an open or a closed circle, and then all we got to do is figure out if the line goes to the left or the right. That is it. And that's the great thing about one-dimensional or just individual number lines that are horizontal like this. Okay, so the first thing, is it open or closed? So we only have the four symbols. You have less than or greater than. If they do not have the equal sign, then it's an open circle at that value, which would represent that the value is not included in the solution set. So let's take a quick one on this. Let's say that I had x is less, in fact, I'll color code this. Let's say I had x is less than 5. Okay, 5 is a nice, easy number to work with. Okay, now the open circle, because this is not equal to, at 5, would tell us that this open circle says that 5, if you put it into the inequality that we started with, would make the inequality false. Because if I replace the x with 5, 5 is not actually less than 5. That's false. Okay? So that's why we would have an open circle to demonstrate that. And if for some reason it had an equal part on it, then we would close the circle, which would then demonstrate that that value would make the inequality true. Next up, it says, is the line going to go to the left or the right? So we just have to look at it as in terms of eating the letter or the variable. So if it does eat the letter, the line goes to the right because the letters are bigger. So everything to the right is bigger. If it goes to the left, it does not. It will not eat the letter because the letter represents any values compared to the number. And if it doesn't eat the letter, that means they're less than that number. Okay. So for example, on this one is showing less than, and since it's not eating the x, is really what we're looking at, saying x is less than 5, which means all values less than 5 are going to make the inequality true. And so we'd say, look, this one is going to go to the left. Again, that's because it's not eating the x. Sorry, my lines aren't so straight, but whatever. The circles tell us where we transition from truthfulness to falsefulness. So like this one, this inequality right here, all these values are true from negative infinity and going from left to right, it stops at 5. That's where it stops being true because it's not equal to 5, and then everything to the right is false. Okay, so right now we shouldn't see lines going to both sides, only to one, and so one side of the number will be true, the other side will be false. Sometimes it'll be the right side will be true, the left side will be false, but it can switch. As clear as that was, let's look at this example. Okay, so this is reading 7 is greater than x, and that's okay, but I see that the x is compared with a 7. So I find 7 on the number line right here, and then I look at my inequality, which is just a greater than symbol. It does not include equals. So there is no equals. So this one is going to be an open circle at 7. So at 7, open circle. Okay. Now we got to determine if this graph will go to the left or the right. This one is not eating x. And since it's not eating the x, the line will go to the left. All right, so on this graph, let's see if I can do this decent. think that's better than my last one. I got to drag this line all the way over until I get the arrow. Now I'm saying that because on the assignment, you're going to click here, and then you're going to have to drag the line all the way over. If you don't drag it till there's an arrow, it's going to mark it wrong because it thinks you just want to stop at a certain spot. We have to drag this over until there's an arrow because all these values on the number line would make this true. Now again, 7 doesn't make it true, which is why it's an open circle. But if you were to compare 7 with 0, which is here, 7 actually is greater than 0. That's true. Or 7 is greater than 5. That's true. All these values on this green, underneath the green number line there, would make this inequality true. And that's what's nice about the graph is it shows us the infinite number of values that would make it true. Anything to the left of -7 makes it true. So that means that this inequality that we started with here, that is what we will end with next time. So next time, it won't give us this. It's going to give us something much bigger than this, like we saw with the equations. Then we narrow it down to something like this, and then we can put it on a graph. So this one reads, x is greater than or equal to 6. Try it out. See if we can graph it, and we'll go over it. So for this one, we see that it's a comparison between x and 6. So 6 is where we're going to start. And the reason that is because that is where the line will change from being true to false. So there's our 6. That's where we're going to start. And for this one, we do see the equal part of that inequality. So that's greater than or equal to. So since it does have the equal part of the inequality, that will be a closed circle at 6. So at 6, boom, just close that circle up best I can there. Well, there we go, that's a little better. All right, so again, we only have 2 parts. Closed circle. Next, which direction does the line go in? Well, this one is eating the x. Which means that it's going to go to the right. Okay, so this one I'm going to show a little different. Sometimes students will show it kind of above, like this. That's fine if you do. If for some reason you're like, I really like it just on the line, all right, that's fine too. But again, we have to drag this over until we see the arrow to indicate that everything to the right of 6, including 6, by the way, would make this inequality true. So again, just test the value. Take the 10, put it in. Is it true? Yeah, 10 is greater than or equal to positive 6 there. Same with 7 or 8 or 9, and then anything beyond that. So this is our graph, either one of these. So a lot of this is just interpretation. Like this one right here, again, where's the circle? And again, we're seeing it transition from going from left to right. You would be true, and then it stops here, and then it becomes false everywhere to the right. But I see that I am comparing a value, x, with -8. Now, I've given myself enough space to put the inequality in here because I don't know what the inequality will be yet. But what I do notice is that here at the circle, it's a closed circle, which means that the inequality should have some kind of equal sign on it. Okay, so I'm going to put an equal sign in there, and then I'll just adjust it to make an inequality as needed. Next thing I notice is that the line is going to the left of that circle, which means it cannot eat the x. All right, so that means it has to eat the -8 there, so I'm going to show it like this, and that's it. Now again, this reads x is less than or equal to -8. Does that even seem true? Yeah, because x would be less than, which is left of -8. So there we go. That is good. Now again, just to reverse this, because you can, if for some reason you wanted to compare -8 with x, that's okay, as long as the inequality still eats the -8, and you still need the equal part on that too. These are exactly the same. They're just shown in different ways. That's it. So this one. All right, again, we see the transition from truthfulness to falsefulness here at 1. So I will be comparing x to 1. Now, this circle is an open circle. So that tells us there is no equals in the inequality. All right, so I can't put an equal sign in here, but I also don't know which inequality it is. But what I do see is that the line is going to the left of that point, which again that means it cannot eat the x. So it needs to eat the 1. All right, x is less than 1. Boom. And that's it. Again, if for some reason you wanted to reverse that, you can compare 1 with x, so long as the inequality still eats the 1. Now this should be true, right? So let's test some values. Let's say -6. So this would read -6 is less than 1. Yeah, that's still true. Or 1 is greater than -6. Yeah, still true, right? Same with -10. -10 is less than 1. That's true. And 1 is greater than -10. Yeah, that's still true. All of that is true. All of these values are true. And since it's going forever to the left, that's why we've got the green arrow there. All right, here's this one for us. Write the inequality for the graph. Take 30 seconds, see if you can do it, then we'll go over it. So right here, I'm going to compare x with -4. Okay, and again, you could do this 2 different ways. Not that it matters, because they're going to be exactly the same. So I'm going to do it twice the same way at the same time. And right here, we have, again, an open circle. An open circle tells us that there's no equals sign in the inequality, okay? So again, I can't put anything in between the x and the -4 yet, but then I see that the line goes to the right. And since it is going to the right, it needs to eat the x. Okay, so in the first one, I would make it eat the x, which would read x is greater than -4. On the second one, I still need to make it eat the x, which would read -4 is less than x. These are exactly the same. They're just shown in different ways. And again, we can check. Again, it transitions from truthfulness to falsefulness. But with 0, make this true. 0 is greater than -4? Yeah, that's true. -4 is less than 0? Yeah, still true. Same with 10. 10 is greater than -4? Yeah, that's true. -4 is less than 10? Yeah, true. All these values would make it true all the way to positive infinity. So that's the last part of our objective right there. I know that an inequality has infinite solutions, and that the graph will tell us all the solutions to that inequality. Now, again, this other stuff, I know the 4 signs of inequality, which will help us with the graph. But in addition to that, we need to know how to solve equations, because next time in, what is it, 6.2? Yeah, we're gonna see more of this equation stuff, but with inequalities instead.